Hi and welcome to Physics High, and today I'm going to go through the questions from the HSC of 2009 and 2010 as they relate to Module 7, which is all about light, or what is light. A forewarning, these questions are from past papers, and so they don't cover all of the outcomes in the current New South Wales HSC syllabus, and predominantly we're dealing particularly with the concept of quantum physics. In this case, we're talking about the photoelectric effect and also aspects of special relativity. But hopefully this should be helpful for you as you prepare for your exams or want to review this particular module. Now, before I start, I really value your support. So if you have the opportunity to buy me a coffee, click the link in the description below to help support the work that I do. So let's get started. Now, our first question deals with the photoelectric effect. Question number 14 says, blue light is found to cause a photoelectric emission from a sodium surface, but not from a platinum surface, and account for these differences. So before we do that, let's quickly review what's going on here. So we have a surface, and that surface is going to be a metal. In this case, it's either the sodium or the platinum. And we have photons of light coming in. Now, those photons will have a certain amount of energy that is associated with it, and each of those photons will have an energy that is dependent on their frequency alone. And that's the reason why we talk about blue light, because blue light has a relatively high frequency, so the energy is relatively high. But the important thing about the photoelectric effect is that the photons cause photoelectrons to be emitted, but it's in a 1-to-1 ratio. So here I've got 5 photons coming in, and as long as it meets the minimum requirement for electrons to be emitted, we're going to get a total of 5 photoelectrons emitted. It's a 1-to-1 ratio. So that's an important fact, and that shows us the quantum nature of light. The energy that the electrons will have is determined by the energy that they receive due to the photons minus the energy that is used to allow them to escape from the metal. And that formula is often referred to as our Einstein photoelectric effect formula, which says that the kinetic energy of my photons is equal to the energy that they receive, our photon energy, minus the work function. The kinetic energy can be discussed in the term of joules, or it could also be discussed in the term of electron volts. Now, why would a different metal not actually emit the photoelectrons? Well, that's because the energy that is received is not greater than the energy, which is the minimum requirement, which is the work function, and that's significant. That's the part that it relates to the material at question. The work function for sodium therefore probably is lower than the work function for platinum. So let's now look at our answers and see if we can work it out. So it says the platinum does not absorb photons. It does absorb the photons, but of course the photons will be absorbed, but then as a result the energy will be converted into heat. So the material does absorb the photons, it's just that it doesn't allow for photoelectrons to be emitted, so A is incorrect. Platinum has more electrons than sodium. That's inconsequential. It is actually of course true, because platinum has a higher atomic number than sodium, but that's not the reason why this occurs. More energy is needed to remove the electron from a platinum surface. I've just related ourselves to that. That's definitely the correct response, but always review the other responses to show your understanding. The intensity of the blue light is not high enough to move the electrons from the platinum surface. Now that's incorrect, and we'll discuss this, and this is often referred to as the discriminator. A and B are pretty clear wrong, but this is the one where students often get fouled up with this response. It says the intensity of the blue light. The fact is the intensity is just about the number of photons. So if I have a higher intensity of light, then I have a higher number of photoelectrons being emitted, but that contributes to the current, but not to the energy of the photoelectrons. That's only determined by HF. And so D is our discriminator, but it's the wrong response, because basically even if we had a super high blue light, doesn't matter how intense it is, it will never remove electrons from the platinum as a result of the fact that it doesn't reach the minimum requirement of the work function. So therefore the answer is definitely C. Let's have a look at number 18. Now this question, we have a slightly long response question, and now we jump straight into the concept of Einstein's special theory of relativity. The nearest galaxy to our Large Magellanic Cloud, with its center located at 1.7 by 10 to the power 5 light years from Earth. Assume that you're a spacecraft traveling at speed of 0.99999, the speed of light, towards the Magellanic Cloud. So let's have a look at part A. You've got in your frame of reference, what is the distance between Earth and the Large Magellanic Cloud? Now it's in your frame of reference, so therefore it's going to be a different distance than, let's say, outside the frame of reference, which is the distance that you and I on a stationary, you or I on Earth would measure. So we're told the distance is 1.7 by 10 to the power of 5 light years, but that's not the distance that is measured from within the frame of reference. And so this is a length contraction situation. So what we have is our length contraction formula, which is that LV is equal to L naught times the square root of 1 minus V squared over C squared. So as a result, you can substitute things in. The length contracted formula, the length value that someone's measuring, they're going to have the contracted. Why? Because they're measuring space outside within a different frame of reference, which is a moving frame of reference. So they're actually getting the contracted length. So our L naught is our 1.7 by 10 to the power of 5. Then of course you multiply that by the square root of 1 minus. Now when you do problems like this, you get V squared over C squared. You don't have to put C squared in there. You've already got the C in there. So you might as well just say 0.99999 and square that. And therefore, when you do that calculation, you're going to get 760 light years. So significantly shorter. What about part B? Well, part B says simply, in your frame of reference, how long will it take? Well, your time is equal to simply the distance that you travel divided by the velocity that you have. Now, we've already established the distance is 760 light years. The velocity, of course, is 0.999999 c. And when you do that calculation, you're going to get 760 years, give or take. Question number 27. We're jumping back to our photoelectric effect here. An experiment is used to investigate the effect of light is shown onto a silver surface, and the results of a maximum kinetic energy is measured. And it says determine the frequency of the highest energy photons used in the experiment. And part B, what effect would changing the intensity of the light have measured on the electron kinetic energy? Let's look at part A. It says determine the frequency of the highest energy photons. Well, the highest energy photons are going to be those with the highest frequency. Now, the thing is, we're given the wavelength. So if you've got all these wavelengths, then the highest frequency is the shortest wavelength. So if you look at all our responses, the shortest wavelength is that value there. And so therefore, it has a corresponding frequency. So if our lambda is equal to 150 nanometers, then our corresponding frequency is simply going to be equal to c over lambda, and that's going to be equal to 2 by 10 to the power of 15 hertz. And that's it. That's all there is to that question. So it's a fairly straightforward question, but it means that you needed to interpret what the table is actually saying. It says, what effect would changing the intensity of the light have on the measured electron kinetic energy? As I stated before in a previous question, the kinetic energy of any photoelectron being emitted is simply equal to the difference of the photon that it's received minus the work function of the metal, which is a linear relationship. But notice what's not there, the intensity. The total energy is totally dependent on the individual photon's frequency. So the answer to the question part B, what effect? None whatsoever. It'll stay the same. We now jump to 2010. A scientist at a particle accelerator laboratory observes a lifetime of a particle, a subatomic particle, to be 1 by 10 to the power of -6 seconds, when it's traveling at 0.9999 the speed of light. What would the lifetime of the particle be if it were stationary in the laboratory? Well, understand again, what we're seeing is we are measuring the time of our particle outside the frame of reference of the half-life of that particle. What we're actually getting, which is this value here, is not the proper time, but the dilated time. So the time dilation formula says that the time, or the dilated time, is equal to t naught, which is its proper time, the time within the frame of reference of the event, divided by the square root of 1 minus v squared over c squared. Now, if we put everything in here, we get 1 by 10 to the power of negative 6. Remember, this is the time we measure outside the frame of reference, is equal to t naught, which is what we're looking for, divided by the square root of 1 minus 0.9999 squared. Now, if you do the calculation out and rearrange that, you're going to get a value of t naught equaling 1.4 by 10 to the power of negative 8 seconds. And that, of course, means the answer is A. Now, where can students go wrong here and will get the wrong answer? One way, clearly, would be to get those the wrong way around. So you can see that the time that we get is significantly smaller than the time we have, because we are seeing the time dilated time. So a student might get them the wrong way around. So they would actually get a value that's longer, and that would be, for example, D. That would be the mistake that they're making. The other common mistake you have to watch out for is forgetting to do the square root here as a result of this equation. So therefore some sort of rearrangement issue. Question number 13. What is Max Planck's contribution to the development of quantum physics? So quick summary. Max Planck was interested in basically how a black body radiates energy, and experimentally it was shown to have a particular type of graph. And that graph, of course, is now known as our black body curve. And it tells us the distribution of the intensities per wavelength across the whole range of wavelengths. And so you'll start here with a small wavelength, or we've got a small wavelength over here and large wavelengths on the other side. That's the way I draw it. And on the side, what we have is spectral radiance, which is the intensity per wavelength or per meter. And the peak, of course, here is determined by the temperature, which is Wien's law. Now, what did Max Planck do? He basically was trying to find a mathematical model that represents this. And by making energy discrete, by making the argument that energy from black bodies must be emitted in discrete or whole number values, in a mathematical way at least, was able to show mathematically a formula that allows us to get this relationship. If we look at the options, he combined quantum wave particle models of light. That's not correct. B, he analyzed the photoelectric effect. No, that's not correct, because Einstein developed the photoelectric effect understanding of the basis of Max Planck's work. So this is not correct. Now, part C. He explained black body radiation and the photoelectric effect using quantized energy. Now that sort of sounds right, but there are a couple of problems with that response. First of all, yes, he understood of quantizing energy, but he didn't actually explain why black body radiation occurred. He actually made a hypothesis, and in fact, for all he was concerned, it was a bit of a mathematical trickery. He certainly did not explain the photoelectric effect. That really is what Einstein did. So this would be a better response for Einstein. D, he hypothesized, now we're on the right track, that the radiation emitted and is absorbed by the walls of a black body cavity is quantized. That is the correct answer. Question 23, now we jump back to special relativity, and in this case we're looking understanding of frames of reference. So a train is traveling on a straight horizontal track, and a student on a train attaches a mass on the string of a ceiling of a train, and the student observes the mass remain stationary in the position as shown. And we have two questions. Why does the mass hang with a string at an angle to the vertical, and the string then breaks and falls? Indicate the path of the mass in the above diagram and explain why the mass has taken this path. Okay, so this is a twofold question and is actually a little bit more challenging as we go into the second part. Why does the mass hang with a string? Well, basically in this frame of reference we have a non-inertial frame of reference. This is a situation where the train is accelerating in that position. That means what we have in effect is two forces are being applied here, causing really this tension to swing out in this direction, and obviously the mass has its weight and has a mass in that direction, and as a result we have a net force according to those things within the frame of reference, which results in this one. That's because the system is accelerating in that direction. It could be the same true if this was going in a circular path, sort of going into the base and around the curve. And so why does it hang? Because the system is a non-inertial frame of reference. It's accelerating and therefore swinging out. And that, in order to get 2 marks, you need to say that it's a non-inertial frame of reference, and you need to say it's accelerating, therefore having a net force acting on the object in that direction. Now the string then breaks and the mass falls. Indicate the path of the mass on the diagram above and explain why the mass has taken this path. Now this is the crucial part. What happens? Well, normally this object will accelerate in the downward direction. And so what we'll do is we'll just look at it from a perspective as if it was not moving across. And so what you end up getting is from a person inside the train, if it was stationary in this sort of situation and just let go, it's going to be accelerating like so and downwards. You'll notice what I've done is I've made it progressively further and further apart, which is what happens, of course, if we just drop it. But from within the frame of reference, this mass is now no longer with the force here of this tension. And so inertia says it will have basically travel at a constant velocity from outside the frame of reference. But from within the frame of reference, you are accelerating. So therefore, you're going to see, at least in the horizontal direction, it's going to be moving away progressively further and further away as the ball's inertia remains back. It's going at a constant velocity, and at least in terms of the horizontal, but of course it is also dropping. And so therefore, you're going to get a straight line path going down like this. And obviously it'll hit the floor, but it's a straight line path because it's accelerating downward, but from your perspective, it's accelerating backwards, giving you that straight line path. And that's why it occurs. Question 31, and now we jump back to our photoelectric types of problems, and says that what is the energy of a photon having the wavelength of 1000 nanometers, and then explain why light having a wavelength longer than a certain value does not produce an electric current of the photocell. Now I'm going to do this reasonably quickly because we've already covered the key concept, and that is that the kinetic energy of a photoelectron is equal to HF minus our work function, and as long as it meets this minimum requirement, this energy, it's going to be released. Now we're asked for that. What is the energy of the photon? But we're only given the wavelength here. So, well, okay, we can work this out. So the energy we're afterwards, which equals HF, is going to be equal to, obviously, the frequency is going to be c over lambda. So we have hc over lambda as the way to work this out. And so now you have 6.626 by 10 to the power of negative 34. That's our Planck's constant. We multiply this by the speed of light and divide this by the wavelength. And the wavelength is 1000 nanometers. So multiply that by 10 to the power of negative 9. And you're going to get an answer of 1.99 by 10 to the power of negative 19 joules. Now I can convert that to electron volts, and all I need to do there is divide that by 1.6 by 10 to the negative 19 joule. Now, this is we've got to be careful of here, and where a lot of people run foul. The 2 most common mistakes of this basic form of question in many respects is A, they substitute in E equals H, and then they substitute lambda in, which is obviously incorrect when given the wavelength. And the second most common mistake is forgetting the nanometers. That's our non-SI unit or non-MKS unit. And so therefore you need to make sure you put in 1000 times 10 to the negative 9 or 1 by 10 to the negative 6 meters correctly for our wavelength. Part B, explain why light having a wavelength longer than a certain value does not produce an electric current. Now, it says explain. And so I always tell my students, when you want to explain something, identify first what the issues are, describe what's going on, and then explain. So let's identify. Well, what happens is that if we have our formula of K equals HF minus phi, the longer the wavelength, the lower the frequency, and the energy is dependent directly dependent on the frequency. So if it's too long, the energy is too low, it's not meeting the minimum requirements of our work function, and thus we don't get kinetic energy being released. So I've identified the issue, I've described what the issue is, and I've tied it in with this formula that we discussed earlier in explaining why a long wavelength may not meet the minimum requirements to get some sort of kinetic energy out of my photoelectrons. Well, that reaches our end for 2009 and 2010 in Module 7. I hope that's been helpful for you. Again, reminder, if this has been very helpful, I value your support by buying me a coffee in the link in the description below. But of course, please press like, share, and subscribe to get my latest updates. My name is Paul from Physics High. Take care and bye for now.